Hello. Welcome to another episode of Maths Dynamics Online. I'm going to work example 15.3. What we have here is a pulley system where we have two masses of unequal mass. One is 3 kilograms and one is 5 kilograms, and we're going to release them from rest and see what happens. We learned from our lessons in dependent motion that, well, depending on the number of pulleys, we're going to have different motion between mass A and mass B. For instance, the velocity could be doubled, or the acceleration, and they could either move in the same direction or opposite directions. Well, we will find out by drawing what we call the datum, if you remember. So I would put my datum right here and call this distance down here SA, and this distance down to here SB. Now let's go ahead and make a relationship with these. I get negative 2 SA from one up here and another one right here. Minus an SB is equal to the total length. And I can take derivatives of that to get my velocities. I get negative 2 times the velocity of A minus the velocity of B is equal to 0. Let's go ahead and take that to another derivative. I don't honestly know if we'll need it, but I noticed on tests that this second derivative was often missed when it was needed, so let's just go ahead and practice. That would give us negative 2 times the acceleration of A minus the acceleration of B equals 0. We can rewrite each of these as 2 times the velocity of A is equal to the minus velocity of B. In other words, twice as fast but in the opposite direction. And this one's accelerating twice as fast but in the opposite direction of B. Okay, well, let's hold on to these equations right here. We should now look at forces. So impulses involve the force integrated over time from T1 to T2. And you should start to notice after doing some of these problems that impulse momentum theory is very similar to what we were doing with work energy theory. This is when we have a force and the amount of time that it's applied over. Work energy theorem gave us the change in energy or velocity whenever we had a force applied over a distance. So work energy is when you know a force and a distance or are looking for one of those, and we would use impulse momentum when time is involved. So we are bringing time back into the picture. I see two masses. I think they deserve some free body diagrams. Alright, on A, I see two tensions going up, and I see mass of A times gravity going down. On B, I see only one tension going up, but we have mass B times gravity pointed down. Alright, what else can we do? Let's go ahead and apply impulse momentum theory. So that would be L1. We're looking at the y direction only in this case, but let's go ahead and say this is on A only for now. So on A, L1 plus the summation of our impulses from T1 to T2 is going to equal the mass times the velocity of A at 2. And I didn't write the velocity because it started from rest. So I just left it as L1. But we could have called this L2, right? And let's only look in the y direction so we can keep the vector signs off. Well, if I look at all my impulses, this will be my summation of all my impulses. On A, I have 2 tensions going up, and it's doing that for 6 seconds. I then have mass times gravity for A. It's pointed down, so I gave it a negative sign. It's also applied for 6 seconds. Anything else? Anything touching it? And gravity, and we're there, right? I think that wraps it up for A, and that's going to equal its mass, 3 kilograms, times the velocity of A at 2. Alright, that looks like an equation that we should hold on to. Let's call that equation 2, and let's call this equation 1 over here. Sorry about that. I'm going to keep the free body diagram visible so I can now look at B and apply L1 plus, or the linear momentum, plus the impulses, the summation of them. In the y direction is going to give us a new velocity on B, or a new momentum. Okay, so let's go ahead and cross that out because it started from rest. If one started from rest, the other started from rest. Their motion is dependent, right? If one velocity is 0, the other velocity is 0. Therefore, its momentum is also 0 to start with. What about our summation of our forces? The forces are still constant in this case, so we don't have to integrate. But what do we have? On B, I just see one tension applied for 6 seconds. And then I see the force pointed down of mass B times gravity. And that's all times 6 seconds. That's going to equal mass B, which is 5 kilograms, all times the velocity of B at 2. Alright, looks like we have an unknown of the tension. Well, solve for T set equal. That eliminates the tension. Okay, then after that you can take this relationship for your velocity. The fact that 2 times the velocity of A is equal to the negative velocity of B, and eliminate that back down into one equation where you can find a final solution where the velocity of B at 2 is equal to a negative 35.8 meters per second. It is moving down. Now that we have that information, you can substitute back in if you wanted to know the tension. So any of these equations you could sub back into and get a tension equal to 19.2 newtons. That tension is positive, right? We cannot have a negative tension, so it is absolutely a positive tension. If you get a negative answer there, you should check your equations, check the signs on your free body diagram or how you translated those to algebraic equations. Alright, take notes on it, finish the problem yourself, make sure you can get through the algebra, and we'll discuss it Tuesday after spring break.